Just as optimization problems, algorithms, and user interfaces need to be well considered and designed, so does a system of hints. We carry over the terminology of hint, even if in this case we mostly work with hard constraints. A hint kind of sounds less stringent, but a good hint is interpretable and effective for both the human and the algorithm. A human must be able to form a mental model of what their hints will achieve, and the system must actually take them into account as reliably and efficiently as possible. Furthermore, through a series of hints, the designer must be able to effect their will with a minimum of frustrating misunderstanding. Consider, for example, the Nullbook and Wolf ILP for drawing octilinear metro maps. Since the approach is constraint-based and a solution is found using a general solver rather than some special-purpose algorithm, it is naturally able to take certain types of user hints, but not others. Any hint that directly and solely involves the existing decision variables can be implemented by adding a constraint, such as fixing a particular variable, or tweaking a coefficient in the objective function. In this particular ILP, there are decision variables that decide for every edge in which direction this edge is drawn. It is therefore trivial to fix the direction of a particular edge and in this way influence the drawing. A hint, as it were. Even though solving the ILP from scratch can take a long time, minutes to hours on real metro maps, slight variations of an already solved instance can often be solved much more quickly. Integer linear programming is slow in general, but solvers typically have a warm start feature that makes them particularly suited for a feedback loop with hints. Consider once more the direction fixing hint suggested before. We claim that it probably does not quite express what the designer wants to communicate. It is overly specific. Indeed, if we use this hint to try to get rid of a particular bend, the algorithm may well decide to introduce a new bend directly at the neighboring station. And this is not unlikely, since it was optimal to have the offending bend in the first place. This particular hint did not constrain the optimization problem in the way the user intended, leading to an updated drawing that contains essentially the same problem as before, just in a slightly different way. Mathematical optimization is often annoyingly good at finding loopholes in problem statements. This results in a frustrating user experience where the user is not able to communicate intent and requires many steps of interactions to influence a recalcitrant algorithm. What's more, these constraints are not just overly specific, they are specific in slightly the wrong way. If a set of these constraints are used to straighten a path, then the algorithm is no longer allowed to rotate the path as a whole, which the user might actually be fine with. We just do not know that based on the vocabulary we have provided. For these reasons, the design space of user hints is subtle and interesting. How can the user's intent be understood properly in the context of the optimization problem? As noted, the direction fixing constraint followed from an implementation detail of the model. In a sensible formalization of the problem, it just happened that these variables were available to have their values fixed. This shows that the intended user interaction and the design decisions for the algorithm are actually linked. As another example of a user interaction that is, let's say, inadvertently possible, the embedding algorithm greedily inserts the edges of the transit network in some more or less arbitrary order. It is easy to allow the user to indicate that a particular edge should be routed early in the process, hoping that this might improve its chances of a good placement. Our prototype used to allow this, but the effect was unpredictable and we consider it a poor hint.